Hey guys, welcome back. All right, so I didn't really hear any major complaints about the last lecture, so I'm assuming that we are all good to go and that you grasped everything from that lecture because I addressed the questions that people have asked so far. If you still have questions about the last lecture, please make sure to add those to the discussion board and I will answer them, okay? All right, so we're going to pick up where we left off last time. We left off last time talking about strong acid and strong base titrations, and we talked about how this is why you guys got so frustrated, right? Because literally 0.1 milliliters shoots you up like 7 pH units for a strong acid, strong base titration, which means they're very difficult to actually observe, but it does mean that you can use a variety of different indicators to actually do those measurements. Well, what happens when you don't react a strong acid with a strong base? Well, for a strong acid and a strong base, the equivalence point is 7. It's not going to be 7 if it's a weak acid strong base or a strong acid weak base. And it's not ever going to be a specific number that you would just know. It's something that you would have to calculate off of the acidity of the weak substance or the basicity of the weak substance, depending on if it was a base. All right, so let's look at this. So this is a weak acid, strong base titration. Notice we're starting a lot higher in pH than we did last time. So let's go back a slide. So here we started at 1, but now we're starting at almost 3. Well, it's the same amount, but it's a weak acid, right? So higher pH associated with that. Also notice that where before, again, I'm going to go back a slide, with the strong acid, it really didn't change that much until at the equivalence point. However, with the weak acid, the strong base is having a much greater effect, right? And that makes sense because it's a weak acid. So as you add strong base, wrong direction. As you add strong base to this, it's going to have a more powerful effect. You also notice that while methyl red worked for our strong acid, strong base, it would not work here, right? Because the equivalence point is way up here between 8 and 9, okay? So because it's between 8 and 9, the only indicator that would work of the two is the phenolphthalein indicator, okay? And you notice that the jump is a lot shorter here as well. Instead of jumping like 7 pH units, now we're only jumping 3, okay, when we get close to the equivalence point. All right, and then again, but look at the top of the curve. The top of the curve, not really a dramatic change because at this point it's already basic and you're looking at the effect of a strong base on a basic solution. So this looks similar to the previous graph, right? The real changes are the beginning of it and the middle. That's where we see the biggest changes here. All right, well, let's sort of briefly look then at the opposite of this. So how do you think, before we even get there, how do you think it's really going to change if we switch around and we look at a weak base versus a strong acid? Well, first of all, where's the equivalence point going to be? Well, when it was a weak acid, strong base, the equivalence point was basic, right? It favored whatever was strong. So if it's a strong acid, weak base titration, then we would assume that the pH would be less than 7. Now, how far less than 7 is going to depend on the particular substance that it is, right? So let's take a look. So here we have a weak base, strong acid titration, okay? Now, let's take a look at what we got going on here. So weak base, and the comparison here, this red line is showing you strong acid, strong base. Okay, so the red line is representing if it was a strong base with a strong acid. The blue line is representing that it's a weak base. So again, you see that it's the part that's weak that's affecting. So you're starting with a weak base, so more acidic, right? And then the acid is having much more of a dramatic effect on the weak base than the acid has on the strong base. Again, representing the fact that weak versus strong. And then you see again, a much smaller range here near the equivalence point, again, about 3 pH units, but in this case, phenolphthalein would be no good. We would need to choose methyl red, and it is, the equivalence point is acidic, right? So it is exactly what we thought it was going to be previously, okay? Now, how does this look when we look at a lot of different ones? So here, and this is why I'm saying you can't just know for sure exactly what one of these curves is going to look like, because here is strong acid, right? Dark red, big shoot up to the strong base. But here we're starting off with weak acids, and weak acids have a very wide range in strength, right? So this is a relatively strong weak acid, so its range is near the equivalence point is decent in comparison to the strong acid. But as these acids get weaker, you notice that this beginning part starts to flatten out more. And by the time we get to this acid here that is incredibly weak, 10 to the minus 10 Ka, it doesn't even have a jump at the equivalence point. It's just a continual increase. Okay, so this one would definitely be really hard to examine using the methodology that we've talked about so far, using indicators and things like that, right? This one as well doesn't really have a dramatic jump. It's just a steady increase. Really, I mean, it looks like above 10 to the minus 6. 10 to the minus 6 works. It has a jump, but anything that's weaker than that just is not going to work for what we want it to work. All right? All right. So now let's look at, say, a polyprotic acid. So a polyprotic acid is an acid with more than one ionizable proton. So here we're looking at phosphorus acid, okay? And you notice that there are different steps. There's sort of two major steps associated with this titration. But what's interesting is this. So take a look at what's happening here. So it's occurring in two steps. So we're starting out here with our pure phosphorus acid, and there's not really much of an increase, not really much of an increase. And then here is where we've lost our protein, our equivalence point, right in this range, around a little over 4. And then we've transitioned to our next acid anion situation here. And then slight increase, and then a more dramatic jump for the last loss of the proton. But basically what we see is with these polyprotic acids, it's the same thing that you see curve-wise, it's just you're going to see it more than once, right? You're going to see it for every single proton that is lost. Okay, so now the last thing we really need to talk about in chapter 17 is solubility equilibria. And this is what your lab last week was based on, right? Because everything we've been talking about to this point is aqueous going to aqueous, right? But what happens when you have a solid that is dissociating into aqueous ions? That's really what we're talking about when we talk about solubility equilibria here, because it's heterogeneous and we know that solids aren't included. And if solids aren't included in the K expression, then that means that there's only products. There is no reactants that's going to be expressed in this K expression. And it also means that we can start trying to figure out how much of a compound will dissolve in a given amount of solution. So based on the solubility rules you learned in chapter 8, you know if it will dissolve or not, but now we're adding a quantitative component to that, how much will dissolve, right? So here's an example. So here we have barium sulfate, solid barium sulfate, and we're going to add it to water, which isn't represented here because it's not going to show up anyways. I guess it could be, but it doesn't matter. But you're taking the barium sulfate, you're throwing it in water, and you end up with aqueous barium ions and aqueous sulfate ions. Again, if we write the K expression for this, we're not going to include the solid because the solid's not going to be there. It's just going to be K equals the concentration of the barium ion times the concentration of the sulfate ion. And we call this K KSP, where SP stands for solubility product, because we're talking about a soluble ionic product that has dissolved. So the SP, again, representing the type of K that we are studying here, okay? So KSP, the solubility product constant, that is the K that we're talking about now. And this is the last K that we're going to talk about. So if you're tired of hearing about capital Ks, we are finally going to move away, all right? So let's write some expressions. So here it says, write the expression for the solubility product constant for CaF2. So that is calcium fluoride. Now, remember, that's an ionic compound. So what you can do here is to predict charges, you can cross up, right? So if we cross up, that says that calcium is a 2+. If we look at the periodic table, we confirm that calcium is a 2+. So the cross-up method is working, and we know that fluoride is -1. So calcium 2 plus fluoride -1. But here's the deal. How many fluoride ions do you have? That 2 means you have 2 of them. So that has to be written in your K expression. So KSP is equal to concentration of the calcium, 2 plus ion, times the concentration of the fluoride, 1 minus ion, but we have to square the concentration of the fluoride ion because there are 2 of them. All right. Let's do one for silver 1 sulfate. All right, so silver 1 sulfate. First thing you have to ask yourself is, what is the symbol for silver? Hopefully you know this. I assume you know this at this point. It's Ag. And the 1 is not referring to the subscript of silver. It is referring to the charge. So silver is a +1 ion. That's also something that you should have memorized because silver is always a +1 ion. And then sulfate is another ion you should know. SO4, 2 minus. So if sulfate is a 2 minus and silver is a +1, then you're going to need 2 silvers to balance out the sulfate. So this is a very similar K expression to what we just wrote, except for this time it's the silver ion that's getting squared, and we just need 1 of the sulfate ions. So you can see how you can do this without writing the dissociation equation. I mean, you could dissociate the compound and then write the K from that, but I feel like that's just losing a little bit of extra time when you don't necessarily have to. And again, I recognize that you guys feel pushed for time on my tests and quizzes, so I'm trying to give you some tricks and hints as to how to regain some of that time. Okay, but remember, KSP is the solubility product constant. That is not the same thing as solubility. Okay, not the same thing as solubility, because solubility is the amount of something that's going to dissolve to form a saturated solution. And remember, a saturated solution is a solution that's holding the maximum amount of solute at that particular temperature, which is often represented in grams per liter, but it could be represented in moles per liter. It doesn't matter. If it's in moles per liter, a lot of times we call it molar solubility. You can easily go back and forth between the two. It's a molar mass conversion, right? A molar mass conversion gets you from gram solubility to molar solubility, okay? So those have units. So solubility has units. KSP is a unitless deal, right? It's just an expression, okay? And it's just, it's a relationship. It's not an actual numerical value, okay? So this is from a previous textbook, but I really like this figure. I think it's very helpful, right? It shows how we can relate KSP to solubility. So the solubility in grams per liter is related to molar solubility. I explained that this is through molar mass, okay? We can go from molar solubility to molar concentration of ions by using stoichiometry. So relating the compound to the ions by looking at the subscripts. Okay, we'll walk through doing that. And then once you know molar concentration of ions, you can get KSP from that. So you can work your way one way or the other, but there's definitely direct relationships between solubility and KSP. Okay? So basically what I'm going to do now is I'm going to let this video end, and the next time you see me, I will be using my phone and a piece of paper, and we're going to work out some questions. Okay, so we're going to start with this solubility and KSP example, and I will see you in just a minute.